Okay, so today we will be discussing some more advanced architectures. Not architectures, it's like about debugging the machine learning models that you implement. So it will involve various curves, understanding of various curves like training curve, cross validation curve, and testing curve. So we will gradually move to understand these curves. We will not go immediately to them. So it will be a complete story behind all these understandings. So we will go one by one and see how we can progress and go to that level of understanding the training, validation, and cross validation and testing curves, and what is the need behind it. So for that, I have to give you some primary feedback, primary understanding of what's going on in behind understanding all these curves. And once we understand this small picture, then you will be able to appreciate why people went to create all these type of curves and what was the need behind it. So to start with, let me just begin with a very small slide which actually gives you a understanding of what's going on when we used to do machine learning stuff. So in machine learning, whenever you plot a data, because you will get some random data from the data set. So the very first beginning, what you will do is you will understand what kind of data it is. So there are two type of data which I have plotted here, and the first one is a sort of linear regression plot, and the second one is a case of classification. So as you can see, when you plot these type of data, one thing that immediately comes to your mind is that the scattering of this plot is non-linear. So in the first case it is non-linear, and in the second case also it's also non-linear. So once you see that these type of plots are non-linear, you try to fit the curves. In particularly for this particular example where it's a regression plot, you try to fit a line in this non-linear data set. So um, so what kind of curve that will fit here? Like, any idea what kind of features that will be required to fit a line here? Can anybody suggest? Like, by seeing this data set, what kind of features you will incorporate in your machine learning model so that it will fit this particular data set? Anybody?
quadratic
Yeah,
features.
right. So by seeing this, you will immediately realize, yes, we can put something like quadratic features here, which is x1 square. So something like that, and it will fit the lines. And similarly, for this type of data set, you will realize immediately that for doing the classification of this particular data set, you will have something like circular feature like this, circular boundary like this. So in order to create this type of circular boundary, obviously you know from coordinate geometry also that in order to create something like this, you have to have a x1 square plus x2 square. So that type of stuff you know by coordinate geometry, and for this particular example it will be y is equal to x square. So this is easy for for simpler data sets. So like this, as you can see here, these data sets are very simple data sets. So um, because of their simplicity, it's very easy to come up with the features that can easily fit this. But how about this one? So you see here on the left side, we have these points, which are these points. These points are the data sets, the dots. And regarding on the same side, during this classification problem, you can see we have two types of colors. One is this one, and another one is this one. So now what decisions you will take regarding the feature vectors, so that you will be easily fitting a line over here, or you will easily classify the points over here. So it's very difficult because the data point which is present in this particular data set, the line which will approximate this particular data set, because it's a regression problem. So the line which approximates this particular data set is very complex. You cannot say that it is x square or x1 plus x2 or something like that. You cannot do that, because the reason for that is not x1 plus x2, it's x1 square or 2x1 or something like that, any other higher polynomial uh, containing only x1, because we have single feature vector here. So um, so coming up with some novel feature is a challenging task here for this particular data set. As you can see, when we fit a line onto this curve, it's very complex. Though it looks like a sinc function, I think you might be knowing it from signals and system, but it's not that. It's somewhere similar to it, but it's not a sinc function. So coming up with these type of features automatically is a challenging task in machine learning when the data set becomes very complex. And similarly, for this particular data set, you can see the same problem arises, because you want a boundary which has to look like this. Like it has to separate here also, and it has to separate here also. So in order to come up with this type of complex feature, it's very difficult from a human mind perspective, that how to come up with x1 and x2 so that it will create these two valleys, or it will separate these two, whereas the other ones will remain same. So nowhere human can understand how to do that. So this is the limit of nonlinear features that we have in case of human understanding. So humans can only understand some way or the other some simplistic nonlinear features like this or this, but not the advanced nonlinear features like this. So this slide shows the limits of human mind in understanding what kind of features it can really work around to create simplistic regression or classification tasks. So once this is over, let me move you to the another slide. So this is basically a typical regression data set that you normally encounter in uh, machine learning tasks. So but there are actually two data sets. One we call as a perfect data set, and the second one we call it as a real data set. So by perfect data set, I mean to say is that it's completely noise free, and it is infinitely large. So as you can see here, there is no noise in this data set, and the amount of data that you can see over here is infinitely large. So you cannot count these points which are there in this particular data set, but it is infinitely large and there is no noise. That's why it's called as perfect data set, and it's not really available. It's very difficult to get this data set. So what we have is actually a simplistic version of that, which we call as a real data set. So what we do is, in the real data set we have some samples of these perfect data set, but noise is also there on top of it. So that is actually a real data set which you normally see, and this is impossible. So these are the two types of data sets that are available, but real data set is very hard to find. So please note that when I will write real data set or perfect data set in the coming slides, you should know what is the difference between the two. Similarly, for the classification data set also, you can have this similar picture where this slide which is on to the left side is actually a perfect data set, where you can see the amount of data is infinitely large and it's completely noise free. Whereas in this case, it's a real data set where we have some samples of this particular data set, but they are imposed upon with noise. So because of that noise, you can see uh, these points which are here are actually scattered around and came outside the boundary. So these points are, see, you can see these points. So these points are coming outside due to the addition of noise, which was added to some sample here and it moved it outside. So that's why real data sets are noisy data sets. Okay. So in our coming lecture, what we will do is we will consider the nonlinear model, which is given over here. It's very simple. It's defined as mx parameterized by theta. So parameterized by theta means it's actually trained by theta. So during the back propagation, this theta will be actually a parameter. So I'm saying it that this particular model M is actually parameterized by theta. and its subscript alpha, and alpha is actually ranging from 1 to till alpha here. So I will what this m alpha x theta is, it's actually nothing but w0. Then we have a weighted summation of all the functions which are f1x or f2x or f alpha x. So you can see that it's weighted. One is w0, then f1x is weighted by w1, f2x is weighted by w2, and similarly it goes up to f alpha x w alpha. So in this particular example, you can see that this particular model has two tunable parameters. First parameter is w0, this one. The second parameter is w1, and all these weights, they are the tunable parameters, but you cannot see any theta here, though I have written theta this side, but this theta is not visible. So can anybody tell me where is this theta if it is not visible here? So this theta will be actually embedded in this particular uh, what do you say, polynomial. So we have this f1x, f2x, and f alpha x. So in these polynomials, this particular data set is embedded. So just a quick feedback, can you hear my voice?
Yes.
Okay. Okay, so this theta is actually embedded in these polynomials. Though it is not able, though we cannot see it, but it is there. We will see when we will go more into the details of understanding this model. So this model is basically a linear combination of these polynomials, which is f1x, f2x, or alpha x, f alpha x, and weights. And both weights and the thetas are parameters which will be tuned during the optimization process. So this curve shows you four different aspects of fitting a curve onto the noisy data set. So on the left side you can see it is fitting by a straight line, and this is a basically, this is representing a dial. So a dial which is moving from this side to this side. So as you can see, when the complexity of the model, we will understand this what it is exactly. But for now, you can understand that if the complexity of the model is very simple, then this particular point will be at this point, and it's a very simplistic model. And during when this dial is at this point, the output of this particular model will be this. So this realization is actually this one, the straight line, but it's a simple straight line because your complexity of the model is very less. It's very simple simple model. So you can say that it is only w0 plus f1x w1, where f1x is actually x. So it's a very simple model. So it's basically realizing that. But as you turn this knob to from left to the right, the complexity of the model will increase. So this is basically showing you the another version of this particular curve, where the more numbers of terms will be added as the complexity of the model increases. And this is again a third snapshot of this, when the complexity of the model is somewhere around here. And when the complexity of the model is very high at this point, then you can see that the model has completely, it's very complex, and it has very high number of alphas. It can be anything like 20, or maybe any, just for a rough guess, 15 or 20. And now you can see the polynomial is very highly complex and nonlinear, and it is completely fitting this data set. So this is showing you a small picture for that, uh, the dial, which is the complexity dial. Okay, so in order to understand the details of all the cross validation or training or any other curves, we have to go through some basic understandings of what's going on behind the picture. So let's discuss universal approximators. So as you might recall that in our earlier lectures also, I have discussed this term universal approximator. If you recall, in my earlier lectures I have already discussed it, but now today we will go in more details. So any complex function. any complex function which you want to actually implement can be formed or can be implemented using linear combinations of f alpha x present in this model m alpha x theta. So as you can see from this equation, what I am saying is any complex model you can implement like this. You have this complex model, right? So this model can be easily implemented with this combination of f alpha x, which is weighted by weights, which is w alpha, w1, w2 or whatever. So this is what this equation is saying. That is, any complex function can be implemented using linear combinations of f alpha x present in m alpha x theta. And also note that this f alpha x, which is given over here, can be of two types. The first type is that it can be a fixed shape approximators, or the second is it can be a neural network. So depending upon this f alpha x theta, it can have two different type of versions. First is the fixed shape, and the second one is the neural network. So to start with, to make you understand what is this universal approximator, I found one video on YouTube, and it's a very good video, and just I will play it so that you will get to know what I am saying. So can you see the video? Is it visible?
Yes, sir.
Okay, so this I found recently, and it's a very what you say, it's a very uh, by seeing this you can easily understand what I am saying in terms of universal approximator. So you see the data set is something like an exponential data set, but how easily the neural network is fitting this line, fitting this data set. So it has completely overlapped onto it by running the training and test laws. This person has created it in some JavaScript, and it's a very good application that he has created. So you see, as he has increased the layers, it's actually fitting the curve more and more. So, so now what he is doing is he's changing the learning rate and all that type of stuff. So all this he is playing with the learning rate. So now he has changed the data set to sine function. So now you see, by using this neural network, how he can fit this data set using the neural network. So he is making it more and more approximate by playing with learning rate or using other different type of activation functions. So this is a particular example of linear regression where it is a non-linear regression where a neural network is used for fitting the data set. And the third example that I will show you is this one. So you see now for this particular example, he is able to fit this line, fit this data set. And okay, so by this you can realize that any function, even this function also, how easily the neural network can fit it. So it's a perfect example or a perfect video of what you say as a neural network approximator. So neural network is able to approximate this particular any type of data set very easily. So that is what I am saying here, that any complex function which is given over here can be implemented using the linear combinations of f alpha x present in this. And this is the example which I have shown you in the video is actually implemented using neural network. We will see both of them. First is the fixed shape and then followed by neural network. Okay, so one more thing that I wanted to say is this particular slide is actually modeling the data set using universal approximator f alpha x. So we will see how f alpha x is used for modeling the data set. So here we have this real data set which I have already discussed, and the real data set is basically noisy data set and limited samples compared to the original data set. So this slide shows you how a decision boundary can be created. So this is actually m alpha x theta, and this is also m alpha x theta. So these are the decision boundaries that is formed using the real data set. And now you see here, if I want to create a perfect data set, what I am doing, is, as you can see, these data sets which were actually original data sets, I made it noise free by setting it onto this line. So all these data sets which are here, or data points, sorry, all these data points which are here are actually moved back to the original line and noise free, and made it noise free, because this is actually the noise that you have. This is the amount of noise you have. So once you do that, you will get a perfect data set which is given over here. And now you can see even that perfect data set also can be implemented using neural networks. So similar observation is here, and this actually shows you how you move from a real perfect from a real data set to a perfect data set. Though it's impossible, but this is just showing you a way of doing it. And this is also a similar picture in case of classification. As you can see here, we have two classes. One is this class and another one is this class. And there is an outlier also which is given over here. And now you can see how the particularly even for this particular class we have an outlier. These are the two outliers, and here for this class this is the outlier. So now you can see how we are moving back the data points to make it noise free. So these are the noise free data sets which we are doing it by projecting it back to the original data set. And now this is the perfect data set realization where we have numerous points. So this is the infinite number of points which are here, and similarly for this class. And the boundary that we are forming to classify these two is a linear boundary. And this example shows you the non-linear boundary which is given over here. Similar observations you can see that how the noise-free data set, how the noisy data set is made noise-free by projecting it back onto the original data set and taking more number of points, infinitely large number of points. You are making it a continuous boundary over here. So it's an example of non-linear boundary. So now what I am trying to discuss today is a universal approximation which we can explain using spanning set analogy. So spanning set is actually a word that has been taken from linear algebra. So what it says is that every vector in a vector space F can be written as a linear combination of F1, F2 till Fb. In our case, it is actually alpha. So every vector in a vector space F can be written as a linear combination of F1, F2 till F alpha. Then we say that this vector space F is spanned or generated by F1, F2 till F alpha. So this is the term when you say that this is basically when you say that what is spanning? Spanning is basically a vector space F spanned by these vectors. These are the basis vectors F1 till F alpha, and we call these set of vectors this as a spanning set for a particular vector but vector space F. And we can also say that this particular vectors, this is F1, F2, F3 till F alpha, this is also F alpha, spans F. So these are the different ways of saying that same story, but I will explain you what this definition means. And one important thing is that this definition which I have said over here applies to functions also. We will discuss that also, but in particularly in linear algebra, these all are vectors. F1, F2, F3 and F alpha are vectors, but if they represent functions, then also this definition will be equally valid. So let us discuss what this definition is. So basically what it is trying to say, what I have written over here, what it is trying to say is nothing but that any linear combination of these vectors, which is F1, F2, F3 till F alpha, if you combine them, it will implement some vector which is y, and this y will be in the vector space F. So this is what this particular lines are saying. So any linear combination of these vectors will implement y, and this y has to lie in this vector space capital F. And as I told you that that same definition will apply to functions. So that's why you can see what I have written over here is W0 plus W1 F1x. So now this F1, which was earlier a vector, is now a function. So same thing applies to functions also. And this function will again lie into the vector space of functions. So, so this is basically what it is telling over here. And if you want to analyze it pictorially, it will be something like this. So as you can see, we have a three-dimensional vector which is given over here. Just a second. This is a three-dimensional vector. As you can see, it is in a cube. You are representing it in a cube, so it's a three-dimensional vector. So this three-dimensional vector can be represented in terms of three different basis vectors, that is f1, f2 and f3, which are along this dimension. So first is in this dimension, second is along this dimension, and third one is along z dimension, and they are properly weighted by w1, w2 and w3. So by properly weighting these vectors f1, f2 and f3, you not only implement this particular vector, but you can implement any vector in this three-dimensional space, which can be this one also, or this one, or this one. So anything. So any vector in three-dimensional space can be implemented by using these three different vectors f1, f2 and f3, and they are also sometimes called as basis vectors. In case of the terminology of linear algebra, if you discuss that, so this f1, f2 and f3 will be the basis vectors. Okay, so now we have the same thing applies to functions also. This is f1x, f2x, f3x, and they are all weighted by w1, w2 and w3 properly, and then it implements a complex function yx, which is given over here. So if you change the weights w1, w2, w3 differently, then you will get obviously some different realization of this function, can be like this. So all these functions will lie into the function space f. So these are the basis functions, and you can realize, maybe if you have studied or not, but I don't know, but if you have studied Fourier series, it is something like that. So in Fourier series, what you do is you decompose a complex function into sinusoidal functions and cosine functions. So that sine and cosine functions, which actually forms the complex function, are called as basis functions because they are linearly weighted to implement the complex function f. So any doubts till now? If you have any doubts, please let me know. Okay. So now what we will discuss is the capacity of these spanning sets. So we will discuss whether what is the capacity. We will discuss what this term is, but to understand it, what we actually want, we want that the linear combination of these vectors should be as close as to the original vector, which is y. So here you see what we want is the linear combination of these vectors to become equal to this particular vector which we want to generate. So this is what it is shown over here, and it's an approximation. You cannot go close to it, but it's an approximation. So this again shows that same slide, as this is this is the vector that you want to approximate, and you see that this is the, if you take only one vector, one basis vector along the x direction, let us say, then what will happen is it will only span vectors in x direction. So every realization of this particular spanning for this particular vector will be in this direction only. So any it will be a scaled version of this. So it can be anything, but it will not be.
Sir,
Yeah.
I think we lost you there. Actually, your voice
Oh,
went on.
now is it okay?
Yeah, now it's okay.
Okay. So so as you can see, if you have a single vector which is on this direction, then you can only have scaled versions of this, but you cannot get this vector. But now if you increase one more vector this side along the y direction, then you can see this vector is realized on this plane and not on the two-dimensional plane. But it is not, and it is very far from this blue. But once you add another vector in the z direction, then you can see how easily it is fitting onto this blue line, which is the original vector over here. So this shows you that how gradually improving, how gradually adding your values of f alpha x parameterized by theta each and each time, like for alpha is equal to 1, alpha equal to 2, alpha equal to 3, you are getting close to the original vector. Similar observations can be done for this particular function also. This is only realizing using this function or this particular basis function, which is this. Then we have two realizations of this, and then we have three realizations of this. So as you can see, as you increase the realizations, this particular original curve can be easily approximated by the generated curve, which is here. So this you can say, this is actually somewhat similar to if you increase the layers of the neural network. So if a single layer is there, it will underfit. But if you increase the layers gradually, it's something similar to that. So as you increase the layers, it will approximate the curve. So that is what this story is in terms of the basis vectors. Okay. So, so this is actually what we are discussing is the capacity of the spanning sets. And we have seen this particular statement, what it says. That is, we want the linear combinations of f1 w1, f2 w2 and f alpha w alpha close to y. This we have already discussed. So, what we want to now realize is that if we want to do this approximation, this particular approximation, what are the possible ways of doing it? The first possible way of doing it is the diversity. If we want, the diversity of the spanning set vectors has to be increased. By saying diversity means the linear independence of these vectors. As you can see here, all these three vectors, 1, 2 and 3, all of them are linearly independent. So the more linearly independent vectors are, the capacity of that particular neural network or any other, or that model will increase. That is m alpha x theta. And the second is the number of them, that is the numbers, how many of them are there. Larger the better. As you can see here, for alpha is equal to 1, you were able to realize only onto the horizontal direction, but with alpha equal to 2, you were able to realize the vectors in the xy plane. But now when you increased it to alpha is equal to 3, then you are able to realize these vectors in xyz plane. So that is basically the number alpha which I am saying over here. So these two things together defines the capacity of the spanning set. That is, what is the capacity? If you say, if somebody asks you the capacity, then the capacity is in terms of these 2 points. And the third one is basically how well these weights, the W1 to WB, and also the thetas, which are actually present in function f. How well these vectors, that is W1, WB, which are these ones. Actually, this is not WB, it is alpha. So how well these W1 to W alpha are tuned, and theta is tuned. And this tuning of the parameters will be done using optimization strategies, which we will discuss later. But the capacity as a whole of the spanning set can be defined in these two terms. Is it okay? Any doubts here? Okay, so today actually I have a machine learning workshop which is conducted by our college. So I will be a bit busy over there, and it's about to start after 5 or 10 minutes. So because of that, I have to close the class today. It will be it was a short class, but we will discuss more details about all these things in our next class. So if you have any doubts related to any of the discussions that I have done till now in on these slides, we have 1 or 2 minutes we can discuss that. So I guess everybody is comfortable with what I have explained till now. Okay, thank you.